All right, strap in everyone, because today we're diving headfirst into a physics paper that really flips the script on one of the most fundamental ideas in physics, electromagnetism.
Yeah, it really shakes things up.
We're talking about a paper called Classical Electrodynamics from the Motion of a Self-Gravitating Dipolar Relativistic Fluid by Sabir A. Rahman, and let me tell you, it's a wild one.
It definitely challenges some very deeply ingrained assumptions about electric charge and how it relates to the universe as a whole.
The big question here is this. What if everything we think we know about electric charge is just plain wrong? What if, instead of being this fundamental property of particles, it's actually something that emerges from something else?
Right.
This paper proposes that charge actually comes from the dynamics of a really unusual fluid.
A very specific type of fluid.
And that's where we need to start with the fluid itself.
Okay.
Rahman's paper suggests that all of space-time, all of it, is filled with this dynamic relativistic fluid.
It's kind of like the luminiferous ether that physicists were searching for over a century ago.
Wait, the ether. You mean that hypothetical medium for light waves that the Michelson-Morley experiment pretty much disproved?
Yeah.
It feels like we're going backwards in time here.
In a way, yes. But Rahman isn't proposing that same old static ether that everyone was looking for back then.
Okay.
He's talking about a fluid that's dynamic, it's relativistic, and it's absolutely crucial to understanding how electromagnetism works.
So this fluid, it's not just sitting there passively.
Yeah.
It's in motion all the time, governed by relativity. That's already pretty mind-bending.
Yeah.
But then there's the matter that actually makes up this fluid.
Right, and it gets even more radical there.
Because we're not talking about normal everyday matter here.
No, we are not.
Rahman introduces the concept of what he calls exotic matter, specifically particles with negative mass density.
Yeah.
Negative mass. So instead of being pulled in by gravity, the stuff would be pushed away by it. I mean, that sounds like something straight out of science fiction.
It definitely is a departure from our everyday experience, that's for sure.
Right.
But the idea of negative mass, it's not entirely out there.
Right.
It actually has a basis in theoretical physics.
Oh, okay.
Particularly in the study of what are called Kerr black holes.
Kerr black holes, those are the ones that are spinning, right?
Yeah, those spinning black holes that have that ring singularity at their core.
I'm vaguely familiar with those.
So the theory goes that if a particle were to cross the ring singularity of one of these Kerr black holes, it would actually emerge on a second space-time sheet.
A second space-time sheet?
Yeah, it's called mirror space-time.
Okay.
And from the perspective of someone, an observer, on a regular space-time, this particle, it would look like it was traveling backwards in time.
Whoa.
And here's the key. It would exhibit negative mass.
So this mirror matter, as you called it, it would have the opposite mass energy compared to the matter that we're used to. And this allows for both positive and negative mass densities within the fluid itself.
Yeah.
But how does all of this lead to electromagnetism?
Well, that's where the structure of this fluid gets really interesting.
Okay.
Rahman proposes that it's made up of what are called gravitational dipoles.
Dipoles, so like tiny little magnets with a north and south pole.
Sort of.
How does that work with gravity?
Think of it this way. Each dipole is like a little tiny dumbbell, with one end having positive mass and the other end having negative mass.
Okay.
And these little dumbbells, they're free to rotate around a central mass, which can be positive or negative itself.
So we've got countless tiny spinning dumbbells filling up all of space-time, each with positive and negative mass components. It's a wild picture, but I'm still not quite seeing how that connects to, an electron or a magnetic field.
Well, that's the remarkable part.
Okay.
Rahman shows that if you start with this fluid model, with all its exotic matter and dipole structure, and you analyze its dynamics, how these dipoles move around and interact with each other, you naturally end up with Maxwell's equations.
Hold on, Maxwell's equations, those are like the fundamental laws of electromagnetism.
Yeah.
You're saying those emerge naturally from the movements of these spinning dumbbells in this fluid.
That's exactly what Rahman's model suggests.
So it's not that Maxwell's equations are wrong.
Right.
It's that they might not be fundamental.
Yeah.
They're more like a consequence of something deeper.
Right, a consequence of the fluid's dynamics.
So instead of electricity and magnetism being like the base reality, they're more like ripples on the surface of this churning fluid.
That's a good way to put it.
It's a huge shift in perspective.
It is.
But where do the actual charges fit into this model? How does a fluid with spinning dipoles give rise to something like an electron?
That's where the idea of sinks comes in.
Sinks?
Yeah, Raman proposes that point charges, like electrons or protons, are represented as sinks in this exotic fluid.
Sinks, like drains in a bathtub. So an electron is basically a whirlpool sucking in this exotic fluid.
It's an analogy, but yeah, that's the general idea.
Okay.
And there are two types of sinks.
All right.
Positive charges, they act as sinks for the positive mass fluid,
Mm-hmm.
and negative charges are sinks for the negative mass fluid.
So an electron would be like this tiny little whirlpool constantly drawing in negative mass fluid from around it, and a proton would be doing the same thing, but with positive mass fluid.
Exactly.
That's a surprisingly intuitive picture.
Yeah.
And this leads to one of the most radical implications of Raman's model, the idea that charge might actually be dimensionless. Dimensionless. But charge is measured in coulombs. It has units, right?
Right. It seems counterintuitive, but stick with me for a second.
Okay.
Remember that basic equation for the force on a charged particle in an electric field. Force equals charge times electric field.
FQE, yeah, electromagnetism 101.
Exactly. And from that equation, you can figure out the units of charge. But here's the thing. Raman's model directly connects the electromagnetic force potential with the fluid's force momentum.
And force momentum has units of momentum, which is mass times velocity, right?
That's it.
Okay.
So if you take the units of force momentum and put them into the equation for the electric field,
Mm-hmm.
and then you take that and put it back into the equation for the units of charge, something really interesting happens.
What's that?
All the units cancel out.
Really?
Yeah. And you're left with charge being dimensionless.
So by connecting charge to the fluid's momentum, the model takes away the need for charge to have its own separate fundamental dimension.
Yeah.
But what does that mean, really? I mean, why should we care if charge is dimensionless?
That is a great question, and it takes us to some of the most profound implications of Raman's model, implications that get at the very nature of reality itself.
Okay, now you've really got me hooked.
But before we go there, let's just take a moment to let all of this sink in, because we've only just scratched the surface of this amazing paper.
All right, you've piqued my curiosity. Let's take a moment to digest all this, and then we'll dive back in. All right, I've had a minute to wrap my head around this dimensionless charge thing.
Yeah.
It's a big change in how we usually think about it.
Yeah.
But you were saying this has even deeper implications, right?
Right.
What's so groundbreaking about charge being dimensionless?
Well, one of the most interesting outcomes is how it might explain the quantized nature of charge.
Quantized nature.
Yeah, so you see, in our current understanding of physics, the fact that charge comes in these discrete units, like the charge of an electron, it's kind of a fundamental mystery.
Right. It's one of those things we just observe in nature,
Yeah.
but we don't really get why it's that way.
Exactly. But if charge isn't actually a fundamental property, but something that comes out of the dynamics of this fluid,
Okay.
then the fact that it's quantized might just be a consequence of how the fluid behaves.
So instead of being this kind of arbitrary fundamental constant, the discrete units of charge could actually be determined by the way this fluid flows and interacts. That's a pretty elegant explanation.
It is, isn't it?
It's like we're getting a more unified picture of physics here.
I think so. And that's one of the appealing things about Raman's model.
Yeah.
It has the potential to connect a lot of seemingly separate phenomena.
And this connection goes beyond charge quantization, right?
Right.
You mentioned it also has something to do with the nature of the sinks themselves.
Yeah, those whirlpools of positive and negative mass fluid that represent the point charges.
Right. What about them?
Well, the paper suggests that these sinks might not just be these abstract mathematical points,
Okay.
but actual physical processes that are happening within the fluid.
What kind of processes? Are we talking like mini black holes popping in and out of existence?
Not quite black holes,
Okay.
but something just as radical.
All right, I'm listening.
Picture these sinks as regions where the fluid is constantly being created or destroyed.
Created or destroyed.
Yeah.
Hold on, wouldn't that violate some pretty fundamental laws of physics, like the conservation of energy?
That's a great question. And it's one that the paper doesn't fully answer.
Okay.
Remember, we're dealing with exotic matter here, particles with negative mass energy.
Right, right.
The usual rules that we take for granted, they might not apply in the same way in this framework.
So we could have these, like, creation sinks where positive or negative mass fluid is just bubbling into existence, and then annihilation sinks where it's disappearing.
Yeah.
And the rate at which this fluid is created or destroyed at these sinks, that would determine the magnitude of the charge.
Exactly. A stronger sink, more fluid flow, bigger charge.
Okay.
It's all about this dynamic equilibrium.
Gotcha.
And the paper actually suggests that this whole creation and annihilation process might be linked to other things we see in the universe.
Like what? Are we talking about dark matter? Or even those multiverse theories that are floating around out there?
Well, those are definitely fascinating areas. Ramon's paper actually focuses on something a little bit more down to earth, something closer to home.
Okay. What's that?
The continuous creation of matter, like what's proposed in the steady-state cosmological model.
The steady-state model, the idea that the universe is always expanding and new matter is being created to fill in the gaps.
Yeah.
I thought that model was kind of tossed aside after the Big Bang Theory came along.
It was, but there are still some unanswered questions about the Big Bang model.
Okay.
And Ramon proposes that this continuous creation of matter could actually be happening at these fluid sinks.
Interesting.
Feeding the flow into or out of those whirlpools that we're picturing as charges.
So this model, it not only connects electromagnetism to this exotic fluid,
Right.
but it could also connect it to the evolution of the universe itself.
Potentially.
That's pretty ambitious. But how does all of this translate to the forces we actually see between charges? Like, we can play with magnets and feel static electricity. How does this fluid model explain that?
Well, that's where we need to look at how the fluid model explains the dynamics between those charges.
Okay.
Remember Coulomb's law, the one that describes the attraction or repulsion between charges.
Opposites attract, likes repel. Yeah, the basics.
Exactly. And in Raman's model, these forces come from the interactions between the flows of fluid going into and out of those sinks we were talking about.
So the whirlpools of fluid, they're pushing or pulling on each other.
Sort of. Yeah, you can think of it that way.
Okay.
These flows, they create pressure gradients within the ether.
Mm-hmm.
And it's these pressure gradients that lead to the forces between the sinks.
Can you give me a more concrete example? I'm a visual learner. I need a picture in my head.
Sure. Imagine two sinks, both representing positive charges.
Okay.
They're both pulling in positive mass fluid from the ether around them, right?
Mm.
And this inward flow, it creates a region of lower pressure between those two sinks.
So it's like two vacuums sucking up the fluid and creating a low pressure zone between them.
Yeah.
And then since nature hates a vacuum, that's what pushes them apart. That explains the repulsion between like charges.
It's not the charges themselves that are repelling each other.
Okay.
It's the fluid dynamics around them.
And this works for the attraction between opposite charges too.
Exactly. A positive charge sink and a negative charge sink, they would be pulling in opposite types of fluid.
Mm-hmm.
And that creates a higher pressure region between them.
So the surrounding fluid would be pushing them together, like squeezing a tube of toothpaste from both ends.
Perfect analogy.
So it's not the charges themselves attracting or repelling.
Right.
It's the fluid flows that are creating these pressure gradients that push and pull the charges around.
Precisely. And from these basic fluid interactions, you can actually derive not just Coulomb's law,
Wow.
but the whole framework of classical electrodynamics.
So all the complex laws of electricity and magnetism we learn about in physics, it could all just be explained by the simple pushing and pulling of this exotic fluid.
That's the idea.
It's a really elegant way to think about it, but this brings up another question.
Okay.
If everything is just fluid sloshing around, where is the energy for all of this coming from? Creating and destroying fluid, these pressure gradients, the forces, it all needs energy.
You're absolutely right. And this is one of the places where the paper goes into even more speculative territory.
Right.
Raman proposes that the fluid itself is what's called self-gravitating.
Self-gravitating.
Meaning that its own gravitational interactions are what provide the energy for its dynamics.
So it's like a perpetual motion machine powered by gravity. Doesn't that
Right.
go against like the laws of thermodynamics? You can't just create energy from nothing.
It's complicated. Remember, we're talking about both positive and negative mass energy in this fluid.
Right.
The rules we usually think about with energy conservation, those were created based on how normal matter works. They might not apply in the same way here.
Okay, fair enough. This is getting pretty mind-bending. We're pushing the boundaries of what we know about physics here.
We are.
But before we get too lost in the weeds, I want to come back to something we talked about earlier, electromagnetic waves.
Okay.
If light is really just a disturbance in this fluid, How does that actually work? How do those spinning dumbbells create something that can travel at the speed of light?
That's the question, isn't it? The very nature of light.
Yeah.
And here again, the fluid model gives a pretty visual and intuitive explanation.
Okay.
Remember that each dipole has that positive and negative mass end. As these dipoles oscillate, they create fluctuations in the local mass energy density of the fluid.
So like a wave of denser fluid followed by a wave of less dense fluid and so on, propagating outwards, kind of like ripples on a pond.
Exactly, you got it.
Okay.
And these density waves, they travel through the fluid at the speed of light, carrying energy and momentum with them, the hallmarks of electromagnetic radiation.
So light is literally a wave in this exotic fluid, just like those early physicists thought with the ether.
It's one way to interpret it.
And of course, it's not the static, unmoving ether that experiments disprove.
Right.
It's a fluid that's constantly in motion with its own internal dynamics and structure.
Exactly.
And it's that constant motion, that interplay of the positive and negative mass fluid that creates everything we associate with electromagnetism.
Yeah.
From, static cling to the light from distant stars. It's incredible.
It is.
But this makes me wonder about the nature of light itself.
Okay.
If light is a wave in this fluid, what does that mean for the idea of photons?
That's a great question and a really deep one.
Yeah.
In the standard model of physics, photons are those fundamental particles.
Right.
They're massless, they don't have charge, and they carry the electromagnetic force.
Mm-hmm.
But if light is actually just a wave in a fluid, then this whole concept of photons as these separate particles, it might need to be rethought.
So photons could just be emergent phenomena?
It's possible.
Like not fundamental particles, but just a result of how the fluid behaves.
And it raises all sorts of questions about wave-particle duality.
Wave-particle duality, the idea that light can act like a wave or a particle depending on how we look at it.
Right.
You think that could be because of the fluid dynamics?
Potentially.
Like the waves in the fluid are creating the wave-like behavior of light?
Yeah.
And the way those waves interact with matter is creating that particle-like behavior we see as photons.
It's an interesting idea.
It feels like we're on the edge of a whole new understanding of how light works.
I think we are.
How it interacts with matter and how it fits into everything else in the universe.
Definitely.
Wow. This is amazing. And these are just some of what comes out of Raman's fluid model.
Right.
But before we get too deep into all that,
Okay.
I think we need to take a breather and let this all sink in.
Yeah, good idea.
We've covered a lot, and the last part of Raman's paper, where he brings it all together, that's where things get really wild.
It is where it all comes together.
All right. Another cliffhanger. You've really got my attention. Let's take a moment to digest all this, and then we'll get to the grand finale of this deep dive. All right, we're back, and I'm still reeling from all the possibilities we've talked about.
A lot to take in.
Exotic fluids, dimensionless charge, the potential connection to cosmology. This paper has taken us on quite a trip.
And we're about to reach the most audacious part of that trip.
Okay, hit me with it.
Remember how we've been exploring the idea that charge and electromagnetism might not actually be fundamental?
Yeah.
That they might be emerging from this exotic fluid?
Right, like ripples on the surface of something much deeper.
Exactly. And now Raman takes that even further. He suggests that even those ripples, those electromagnetic forces, might themselves come from gravity.
Wait, gravity? Like the force that keeps our feet on the ground?
Yeah.
You're saying electromagnetism, the force that makes our phones work, might just be a different form of gravity.
That's exactly what he's proposing.
I mean, how is that even possible?
It all boils down to the idea that the fluid is self-gravitating.
So the fluid is pulling on itself, and that's what's creating all this motion and those pressure gradients that lead to the forces between charges.
That's the idea.
It's like a cosmic dance, with gravity calling all the shots.
It's a beautiful image, but it does raise some questions.
Like what?
Well, our current understanding of gravity comes from Einstein's theory of general relativity, which talks about the curvature of space-time.
Right.
How does a self-gravitating fluid fit into that?
That's what I was wondering. Are we talking about warping space-time on a tiny scale to create those sinks and flows? It's tough to picture.
It is, and this is where Raman's model really pushes the limits of what we know.
Okay.
He suggests that the fluid self-gravity isn't just about curvature, it also involves something called torsion.
Torsion. Is that like a physics term?
It is.
I thought that was something you did in yoga.
Well, in physics, torsion means the twisting of space-time as opposed to the curvature.
Interesting.
It's a concept that we don't fully understand, and it's not really a part of standard theories of gravity like general relativity.
So we're not just bending space-time, we're twisting it.
Yeah, think of it like wringing out a wet towel.
Okay, I can see how that could lead to some strange things happening.
Exactly. And Raman proposes that this torsion, together with the fluid's dynamics, could be what creates the electromagnetic force.
So the twisting of space-time caused by this exotic fluid is creating the push and pull between charges that we experience as electromagnetism.
That's the idea.
It's definitely a wild thought and probably needs more research.
Oh, absolutely. We're in uncharted territory here. Our current theories of gravity and electromagnetism might need to be expanded or even completely reimagined.
That's what makes theoretical physics so exciting.
It is. It lets us explore these radical possibilities and see where they lead.
So, big picture, what are the main takeaways from all of this? What's the big idea that Raman's paper is trying to get across?
I think the most important thing is that it makes us rethink the fundamental nature of charge and electromagnetism. It's asking us to consider the possibility that what we see as fundamental forces might actually just be emerging from something even more fundamental.
A reality where gravity, in a way we don't understand yet, plays a central role.
Exactly. And that underlying reality could be this exotic fluid filling up all of space-time.
This dynamic ether that's bending and twisting space-time because of its own gravity, creating the patterns of forces that we see as electromagnetism.
That's it. It's a massive shift in perspective, and the implications are huge.
I can imagine.
If charge is dimensionless, if electromagnetism comes from gravity, it could completely change how we understand the universe.
Yeah.
And maybe even lead to a more unified theory of physics, one that brings together all the fundamental forces.
It's crazy to think that all the complexity we see, electric and magnetic fields, light, the interactions of charged particles, it could all come from the simple motions of this exotic fluid.
It is a pretty stunning thought.
Like a giant cosmic tapestry woven from gravity.
It's a beautiful image. And even though Raman's model is still theoretical, it shows the power of human curiosity and our drive to understand the universe.
It definitely leaves us with a lot to think about.
It does.
If even part of this model is right, it means we're only just starting to grasp what reality really is.
Absolutely. There's a whole universe out there, hidden beneath what we see every day, just waiting to be discovered.
This paper really highlights that. With its bold ideas and unique approach, it shows that the journey of scientific discovery is far from over.
Well said.
This has been a deep dive for sure, and I think we've all come away with a new sense of wonder about the universe and all its mysteries.
Me too.
To everyone listening, keep exploring, keep asking questions, and never lose that curiosity. We'll be back soon with another deep dive into the unknown, but until then, keep those minds thinking.